In the previous video, we learned how to add and subtract vectors, with the main focus being on adding and subtracting vectors from the matrix perspective. You have two vector matrices. How do you add or subtract them? Okay, now we also did get a visual look at the meaning of adding or subtracting vectors from a graphical perspective using vector arrows. However, all of the vectors that we worked with were defined based on a coordinate system, were contained within a coordinate system. The vector space of the vector had a coordinate system, which means that the vector has a vector matrix associated with it. Because we have this coordinate system here, this rectangular coordinate system in this case, this vector has a vector matrix, Vx, Vy, Vz. Okay, now, for any situation where you're dealing with vectors that are defined based on coordinate systems, so there's vector matrices, then if you're going to want to perform some operation, addition or subtraction, or scalar multiplication of a vector, dot product, whatever, you're going to go ahead and just do it with the vector matrices. Why wouldn't you? It's immensely easier. You get the resulting vector or information you need. So if you add two vectors, let's say you get this new vector, and there you go, you have your vector. Just go ahead and plot that vector in the coordinate system. Now, but as we've talked about, you can still think about these processes graphically, even if you have coordinate systems, because vectors within coordinate systems, in general, from a formal perspective, these vectors are still drawn to scale. So if you have this vector v and this vector p, and you want to think about adding them, well, even though they have coordinate systems, you can still think about doing something like the head-to-tail method to get v plus p from a graphical perspective. This is v plus p. Okay, if we took these two vector matrices and added them and got a new vector and then plotted that vector, this is the vector we would get right here with this length in this direction. But what would we do if these vectors weren't defined within a coordinate system? Okay, so we've got these two vectors here. Let's say they're two force vectors or something, two velocity vectors maybe. These are 3D vectors. We're in some 3D space. This isn't a coordinate system. I'm just trying to indicate 3D space here. The vectors are drawn to scale. We know the magnitudes of each vector, and we know the directions. The directions correspond to the directions that the arrows are drawn in the space. Even though there's no coordinate system, we can still see what the direction is, right? P is like going sort of down and maybe 40 degrees west of south and maybe out of the page a little bit. Okay, but there's no coordinate system here. This is truly graphical. So how do we find v plus p? Well, okay, we know from a graphical perspective how to add or subtract vectors. So let's do the tip-to-tail method. Okay, and so with that, there is v plus p. There it is. That's the vector. It's a 3D vector. It's kind of coming, looks like it's coming out of the page a bit to the left and down. Okay, but what's the length of this vector? What's the magnitude of this vector? What's the direction of the vector? How do we analyze this? Well, for a situation like this, whether or not you use the tip-to-tail method or the parallelogram method, it's all going to come down to you're going to need to solve a triangle. And how do we solve triangles? Well, if we're dealing with a right triangle, then just the Pythagorean theorem and the trig functions. But for any triangle, any general triangle, acute, obtuse, whatever, we use the law of sines and cosines, which are just these equations that relate the angles and side lengths of any kind of triangle, not just like a right triangle. And so that's what we would do. We would know the length of the two vectors. We'd know their magnitudes. And then perhaps we'd also have some information about the directions relative to certain lines, maybe relative to the up-down line or something like that. Just based on whatever information we have, we solve the triangle, getting the length of this line or the magnitude and just whatever directions we need, whatever angles we need and directions we need. So like this would be angle A, let's say, angle B, angle C, then capital P, capital V, and capital V plus P would be the side lengths and corresponding to the magnitudes, and that would be it. Law of sines and cosines here. It's just set up to where for a general triangle, you lay out the parameters this way where an angle and side length opposite that angle have the same letter, just one is capitalized, one is lowercase, right? Side opposite angle B is side length capital B, side opposite angle C is side length capital C. And then with that notation, you've got the law of sines and law of cosines. Okay, and if you need a review or just actually need to learn for the first time how to use the law of sines and cosines, go check out the trigonometry playlist.